Good morning. So, continuing our circle journey, we are Unit 2, Classwork 11, Intersecting Chords in a Circle. So last week, when we investigated intersecting lines in a circle, we found angles. This week, we're going to find segment lengths. And if you're looking at the classwork here, you see that we will be using the quadratic formula. You can factor any way you know how to factor because some of you came from different places, but the quadratic formula always works. So I wanted to give a quick review of that, and then I'll let you know which problems are the honors problems as we go through. So we need to identify A, B, and C in the first equation. So I see that the coefficient of x is 1, that invisible 1. So A is 1, B is 6, and C is negative 40. We know x equals, I always say opposite B. So opposite B is 6 plus or minus square root B squared, 6 squared, minus 4AC. So it's going to be 4, A is 1, C is negative 40. And all of that over 2 times A, which is 2 times 1. And then put that in. We've got x equals negative 6 plus, now I'm going to break this into two equations where it's opposite B plus and opposite B minus. 6 times 6 is 36. Negative 4 times negative 40 is positive 160. I'll move that over 2. And x equals negative 6 minus 36 plus 160 all over 2. X equals, all right, 36 plus 160 is 196. Square root of 196 is 14. So x equals negative 6 plus 14 divided by 2. X equals negative 6 minus 14 divided by 2. So our values for x equals 4 and x equals 10. Those would both work. The next one, A equals 2. Let's do a squiggly. Here we go. All right, we've got A equals 2, B equals 7, and C equals negative 30. X equals opposite B plus or minus B squared. I'm just going to do 7 times 7, 49, minus 4 times A times C all over 2A. X equals negative 7 plus, so we're going to break it into the two equations, 49 plus 4 times 2 is 8, 8 times 3 is 24, 240 divided by 4. X equals negative 7 plus 49 plus 240 divided by 4. And 49 plus 240 is 289, and the square root of 289 is 17. Sometimes you'll get a radical, and sometimes you'll get a nice whole number. So x equals negative 7 plus 17 divided by 4. X equals negative 7 minus 17 divided by 4. And our 2x values, x equals 5 halves. You can put that in decimal. X equals negative 6. So that's our quick review of quadratic equations. Those will come up this week. All right, here we go. What if two chords intersect inside a circle? We're going to look at two ways of finding segment lengths of chords. The first way lends itself to the actual theorem, but the first way, what we're going to do is how we've started with transformations and going back to our similarity unit. So we're going to create two triangles here. Triangle BE. Hold on, I gotta let my cabinet. All right, we want to create two triangles. And triangle AEC. We're going to add line segments BD and AC. So here we go. We're going to just draw in line segment BD and AC. We want to compare angles B and C and determine which one's bigger. Well, if I look at angle B, it's an inscribed angle, and its intercepted arc is AD. But we also know that angle C is an inscribed angle with the same intercepted arc. So the triangle that contains angle B looks bigger, but the angles themselves are the same. So angle B is congruent to angle C because they share arc AD. And if we can share that arc, can angles A and D share arc BC? Yes, they can. So we're going to go these two angles. Angle D is congruent to angle A because they share arc BC. So how are those two triangles related? Well, we can say that triangle BED is similar to triangle AEC by angle similarity. And if we know that the triangles are similar, then we know then that the sides must be proportional. They're going to have the same scale factor. So my question here is, what transformation took place? Usually when we have the bow tie, it's because we've had a rotation. But in a circle, when you cross chords, those angles that you create are going to share arcs. And because of that, this is a reflection. Which means then, I'm going to grab some color here. Which means then that BE and EC would be a ratio. And it means then that D, ooh, it's sliding on me. D, there it goes again, I don't know why it does that. We get the idea. Boom and boom. Those go together. If we were going to set up a proportion, we would do green over green and pink over pink. So let's write out that proportion real quick. I would go BE over CE equals, let's go back to the big triangle, DE over AE. Pink over pink, green over green. So we can just start filling in what we have. They do the letters opposite. I flipped them. So we have 6 over CE equals 8 over 4. We've got 8 times CE equals 24, which means CE equals 3. One way of finding missing lengths of chord segments in a circle. Let's practice that together. For each of these, we're going to use method 1. We're going to create similar triangles and set up proportions to solve for x. So let's go ahead. Does it matter which 2 triangles I make? No, because if I've done triangles this way, the angles would still share the same arc, and we would just set up proportions, but they would be the same proportions. Okay, let's go back to where I was. And yeah. All right, so it's going to be 8 over 6, but remember, these are all reflections. 8 over 6 equals 12 over x. We've got 8x equals 72, x equals 9. 14 over 18 equals 21 over x. Over x, 15 over 9. We've got 15x equals 90, so x equals 6. Boom, boom. 8 over 16, 9 over x. X equals, you look at that one, 18. All right. Oops. Oh, I hate it when it does that. So sorry. I don't know why. Okay, here we go. This is where it's going to start getting a little tricky. It's going to be 18 over 3x plus 6 equals 14 over 3x. When you do the cross product, oops, that's not 33, 3. When you do the cross product, you need to remember to distribute. So we're going to have 18 times 3x equals 14, 3x plus 6. 54x, 14 times 3, 42x, 14 times 6, 84. Subtract the 42 from 54x, you've got 12x equals 84, which means x equals 7. And here we go, 14 over 10, 14 over 10 equals x over, what is that, 15, cross product, 10x equals 210, so x equals 21. All right, so this is one method, making similar triangles, setting up proportions. However you do this is fine with me. Look at my box is sliding with me. I hate it when it does that. However you decide to do it is fine with me, but this is the actual theorem here. So if two chords intersect in the interior of a circle, then the product of the length of the segments of one chord is equal to the products of the length of the segments of the other chord. Here's one chord. So what this is saying is E times A, or EA times EB equals EC times ED. So we can just skip the proportion and know that we'll be multiplying correctly if we just multiply the chord length. So let's do this one together. Instead of drawing triangles, I'm going to say directly x times 6 equals 4 times 3. Let's do the triangle so you see it works. X over 4 equals 3 over 6. Look at that. 6x equals 12. 6x equals 12. So this is the actual theorem, but if you feel more comfortable making similar triangles and setting up the proportions, please do so. X equals 2. Here we go. This one here. All right, it's going to be x plus 3 times x plus 1. We just got hard crazy quick. Equals x times x plus 5. We can use area model, distribution, FOIL, however you combine two binomials, however you multiply those. But it's going to be x squared plus x times 1 is x, 3 times x, 3x plus 3. That's what you'd get if you FOILed, equals x squared plus 5x. Looking at this, I noticed that the x squareds will cancel. That won't always happen, but in this case, the x squareds will cancel. So on the left side of the equal sign, x plus 3x, 4x plus 3. On the right side equals 5x, subtracting a 4x from both sides, x equals 3. This is us. Now we might have some factoring using the quadratic, but we're going to have nice numbers. There we go. We're going to use method 2 here to find the length of the chord segments and setting them equal to find x. So 10 times x, or x times 10, however you see it, and 5 times 12. So 5 times 12 is 60. 10x equals 60. X equals 6. We're going to come back to number 2. Let's go to number 3. 6 times x, 4 times 15. 6x equals 60, x equals 10. All right, let's go look at the hard ones. X times x plus 10. All right. X plus 1 times x plus 8. All right, on the left side, x squared plus 10x. On the right side, sorry, I look so crazy right there. X squared plus 8x plus x plus 8. Again, we're lucky in this case that x squareds cancel out. And we have 10x equals 9x plus 8, subtracting 9x from both sides, x equals 8. Best video ever, my cat and Alexa. Here we go, here we go. One more practice here. X times x plus 12 equals x plus 6 times x plus 2. I'm doing multiple of these because I want to make sure that we have good practice before you have to do it on your homework. Doing the FOIL or multiplying the binomials. X squared plus 12x, remembering to distribute. X squared plus 2x plus 6x, 6 times 2 plus 12. Again, lucky ducks we are. The x squareds cancel out. We have 12x equals 8x plus 12. Subtracting 8x from both sides, 4x equals 12, x equals 3. And there we go. You're really figuring exactly to these kinds of problems. We give a look-see at the homework real quick. There's one good factoring problem. Nope, not there. I think we wait until next time where we use our quadratic formula in homework or classwork. All right, good luck. Let me know if you have questions.